This is Shakil Ahmed. In this tutorial, we will discuss about linear regression. We start with simple linear regression. Simple linear relationship is a statistical method to assess the association between two quantitative variables. Basically, we might have categorical or discrete independent variable, but the dependent variable, the response variable, should be continuous and should follow normal distribution. So uh, we have simplest form of y is equal to alpha plus beta x, where y is the dependent variable and x is the independent variable, and intercept and b is the slope coefficient. When we estimate the regression, we get a and b. That is the intercept. Intercept is basically the value of y when x is 0, and beta is the rate of change uh, for unit change in x in y. When we change a unit, one unit in x, how much, at what rate y changes, that is called the beta intercept. So these are the basic assumptions of simple linear regression. We should have linear relationship between dependent and independent variable. Uh, that is, it should be linear, and dependent of error term, we should have an independent sample. The individual's observations are should be independent with each other. And the homoscedasticity, that is the assumption about the error term. Error term should be constant. The variance of error term should be constant for uh, different values of x. That should not depend on the independent variable, or should not vary individual to individual. Basically, given an individual y, the variance of y given x should be constant. And in the normality of error, the error term should follow a normal distribution. This assumption is required to test about the uh, test whether beta is equal to 0 or not. 0 means there is no effect of x on y, and there should be no multicollinearity that is required for multiple linear regression, but for simple linear regression, we don't need this assumption. So here we start with a simple linear regression. We need to import the statistical model using stats model.ap, and you also need to import numpy, and then consisting age and glucose level. We just want the relationship between age and glucose level, and the age just need to convert age as numeric. If it is already numeric, then we don't. If there are missing values, then we need to check for missing values. Often as if there are missing value in these two variables, which then with your mean, I will need to drop them. And then these are the clean data. We have y and x, and then x, we can add a constant with the x, and we get an x matrix. We should have a column of ones in x so that we can produce a intercept as well. Other softwares don't require this. For example, in R, we don't need to do this. We just need to put x1 next to x3, but we not a constant term. But here in Python, we need to do this. We need to create a column x, include a column of constant in our x matrix, and then create and fit the ordinal uh, ordinary least square method. This is called ordinary least square OLS model, and this is From statistical model, we just using the OLS and Y and X response variable. You can see the distribution of Y and X consists of two rows. One is and the other is the order of X here. Just a frame with shape, 5, 1, 10 observations and two columns. Can also view using this option here. But we don't need to do the and the result model fit and summary of the result. Summary of the result, it includes all the things we need. Basically, what we need is the coefficient. This is the intercept, and this is the age effect of age, and it is the value when age is 0, and this is the uh, change in average glucose level when we change a unit change in x with 1 year change in x change in age will cause a 0.47 increase in the glucose level, and this is the standard error, and this is the t basically suggest the significance of the test, whether the beta is equal to 0. Basically we test whether beta is equal to 0 or not. So this is statistically significant, means the beta is not equal to 0. The H naught is rejected. And we also have the R square value of statistic. These are all the model fit criteria. A better value of these uh, statistic means that the model is best. And we also discussed the assumptions in detail. The Darwin-Watson test, the George-Berra test, and the kurtosis of the residuals and all the things. Check the assumptions one by one. First is the check the linearity. So you just made a residual plot with basically the residual changes with x age, and that tells us the linearity of the model. And this is the residual plot for residual versus age plot. And check if it's scattered around the 0. If this is random, then it's um, there is a pattern, then there is a non-linearity. In this, we can see some non-linearity. We can check the assumptions of independent, the variable should not depend on its that value. That is basically the observations are independent. We can check this using the uh, Darwin-Watson test, and how we can perform the Darwin-Watson test. From the summary statistic, we are just from this table. You can see here the Darwin-Watson statistic. It is 1.967, and you can also report the p-value. So this value should be if this is around 2, it means there is no autocorrelation. If this is far from 2, then there is an indication of autocorrelation. So here the Diagnostics statistics is 3.07. So it means there is an indication of autocorrelation in this data set. And then homoscedasticity can be checked using the test of residual. And this is usually just Doraj pagan and then residual and X. And you can write, just name it as BP test, and the p-value you obtain using the first value of this result. If you want to print whole result, then you can just print and don't write BP test. And here I'm just reporting the p-value, and on the p-value we can decide whether we need to reject H naught or accept H naught. Reject H naught means there is evidence of heterogeneity, and fail to reject H naught means there is no significant evidence of heterogeneity. Of heteroscedasticity. And you can also check the homoscedasticity using a separate of your residual plot you have already obtained above. And then normality of the term can be checked using the Anderson-Darling test. Anderson-Darling test, just we use the command normal and Anderson-Darling test, AD, and then residual, and then and the p value again we extracted the p value and then bring the p value, and then on the basis of value we reject the null hypothesis. It means residuals are not normally distributed. If we accept the null hypothesis, it means residuals are normally distributed. So here the p 0.00, it means residuals are not normally distributed. Finally, we can plot a quick the normality of the residuals. Here we can easily say that there is an indication of a non-normality. And not, no multiplier can be checked using the autocorrelation. Basically, we can check with VIF factor, but for simple linear regression, we can't. We don't need to check the multicollinearity. Basically, multicollinearity is the relationship between and high or perfect correlation between the covariates or the independent variables. So we need to check that when we are dealing with multiple linear regression. So in next video, I will show the simple linear regression as a tool of machine learning method, and we can predict the values using. We can separate the values using the train and test set, and then we predict the test set using the train model. So we will discuss that in our next video. So don't forget to subscribe if you still not subscribed my channel. Thank you.